because probably radio service is not known as Red Hat or the other speakers today, let me just introduce also our company quite quick. My name is Christian, I'm one of the four founders, and we at Radio Services, we are an IT security and IT risk management company in Vienna. We are focusing on managed security services, which means we are analyzing what's going on at our customers. We have banks, we have financial insurance companies, we have different other companies that are aware that they are probably not that good in IT security, but better in their main field of banking or insurance. You see here a short introduction of our website. So what Andreas will talk about is probably one of the interesting fields that we are working on. How to get into the direction of analyzing what's going on in network without writing rules or writing different detection signatures, but more going on the behavior side. And this is also where radio service is focusing in the future. So from rules and signatures more into the anomaly detection when it goes to statistical models and algorithms. And we are always looking also for bright minds and guys that would like to work in this area. So maybe afterwards we can talk also about opportunities and also have a look at our website if you like and keen on working Ruby on Rails, Python, and other things in the analysis field of IT security. So I'll hand over to Andreas, which is head of research at Radio Services, and feel free to ask us any questions immediately. Thank you.
Okay. This is interesting without sitting in front of the screen. Okay. I'm going to talk about anomaly detection. In this example, in easy time series data. I'm going to present an easy example. It should be scalable to something more complex. I will go into detail about this a little bit. No problem. Okay, what kind of data am I talking about? Data like this. Let's pretend, I mean this data is generated, but let's pretend it is some graph about number of connections in a network. Like, I don't know, SSH connections from server outbound, something like this. And the x-axis is actually days. So you can see that there's fluctuations in the data. When you have data like this with a strong trending function or seasonality, then you have a problem estimating this distribution to actually talk about anomaly. And anomaly detection basically means that you try to find a middle ground in your data, find a baseline for this data, and tag events that are far out of normal scope. So as you can see, there is a lot of fluctuation. That means that the average is shifting based on time. This is the way that I generated this data, but you see this in network graphs all the time actually. What is anomaly detection? Anomaly detection provides a model that can decide between tagging something as normal and tagging something that I don't expect to see, basically. When you have data like the one I showed you, like this, and you estimate a flat model, you got problems. The problems are shortly outlined here. You can have high false positive rate. That's annoying for the guys looking at the data. You can have high false negative rate. That is probably not so good as well. And quite often you get both, which is really annoying. Like really annoying. So what you should do, you should try to capture what the data actually looks like. And why do we care? I mean, we are a risk security company. What do we get from this? We want to track changes in behavior, basically. So we want to see if some host in a network switches from I do the occasional HTTP connection to I'm now a server. Because if the customer didn't start a server there, he probably doesn't want that. He probably doesn't want to run, I don't know, a mail server on his DMZ network. That's probably not cool, and he probably didn't intend to. So we try to track behavior. Yeah. And what I show here is very basic stochastic modeling. Why will I do that? Well, I hope I will explain that. It gets more interesting afterwards. There is, in these very basic examples, some assumptions that I did about the model. For instance, that count after is Poisson distributed is quite often. Yeah, I wrote it down. In this case, the parameter of the Poisson distribution depends on weekday, but I know that because, I generated the data, but it's a fair assumption in the network. Yeah, and since I'm using a Bayesian model, I can explain that later if someone is interested. Is interested. I did some prior assumptions as well. Yeah, mathematical notation rather short. Now the interesting part, I'm doing this using PyPsys-3. This is a framework that allows modeling of stochastic data. It is basically a stochastic programming interface in Python. It's in the version 3 quite alpha. You should probably not use it in a stable environment at the moment. There is an older version that can do exactly the same, it's just a little bit ugly on the syntax side. So they actually redesigned it. Yeah. What else am I using? I'm using pandas, NumPy, SciPy, scikit-learn, and Theano. If people are interested, I can go over what those projects do. If someone does numerical calculation in Python, he probably knows that. So, yeah, getting started. The interesting part is down here. As you can see, I define a model here. Very basic. When you look at this, I say my data is Poisson distributed. Poisson distribution has one parameter. And I say it's dependent on my data, on my actual measurements. Or rather, on my input data. And my input data in that case is the day, like Sunday, Monday, Friday, whatever. And I model something here, which means I build this Poisson model as a not evaluated equation, as something that can be optimized and toyed around with. And what I get from this, I will just skip over that. I get a likelihood result for my model. Not so interesting. I do MonteCarlo Simulation. Again, I can actually explain that afterwards. But what I really get is something like this. MonteCarlo Simulation is basically taking a sample of measurements, like our time series before, and toys around with it and generates a very, very large number of samples to do statistics on. And I get my estimates for daily average values. And even better, I get a distribution for daily average values. And I can then decide things like this. If we receive a connection count of 25 on a Wednesday, is that okay? I got here, Wednesday is this value. I have an average of 21 connections per hour on Wednesday. So, is 25 normal? Well, I can now use the equation from before and get a p-score of 17.3% for for a 25 count, which basically means that about every 6th event that I measure will be 25 or higher, which is okay. Do I get, let's say I get a connection count of 25 on Sunday? How about that? Is that normal? I do the math again, put it in the equation, and get this likelihood, 2.8 times 10 to the minus 9th, which means that seeing a 25 connection count on Sunday is actually an order of magnitude less likely than winning Euro million, which is probably quite unlikely. You probably don't see that very often. How does that look graphically? We estimated now 7 different thetas or 7 different Poisson distributions for every weekday, and we can produce a probability mass function for it. And we see now for Wednesday, the center is at 21, 25 is right in the middle of our data. That is quite cool. For Sunday, well, our center would be here. 25 is way out there. So we will tag this event as anomalous. Well, if people do statistics, then they will probably ask, why don't I do that or why do I use something like pi-MC3, why do I use MonteCarlo sampling for it? The answer to that is, well, in this example, you probably wouldn't. You can evaluate that using maximum likelihood quite easily. But what else can you do in pi-MC3? If you're interested in anomaly detection, if you're interested in statistical analysis, MonteCarlo can give you a lot more. MonteCarlo can give you direct estimation of very complex models. Like, I don't know, do any of you have any knowledge about regression analysis or time series analysis? Anyone here? Okay. When you do that, and regression in general, you often have the problem of heteroscedasticity. I don't know if that's a topic here, but I guess it is. That means that variance is not the same over all your data, which basically screws with your t-scores, it screws with what you actually can get from a model. And the normal frequentist way of solving that is to estimate things like a variance matrix and then to two-stage weighted least squares and toy around with robust estimates and do complicated things like ARMA models or ARIMA models or whatever. And the beauty about this is you don't have to. I know I skipped over this a bit, but when you look at the model I built, my assumptions here, where is the data pointer? I don't know. No, whatever. My assumptions here are directly in the code, which means if I have a normal regression model that basically is the same like this, only that assumes an all distribution here with 2 parameters, mu and sigma, and not just 1 parameter, then you could simply put an equation in for the standard deviation. You don't need to estimate some weights, you don't need to estimate, I don't know, robust standard deviations or whatever. You can do it directly. You build a model that looks like this. You say my mean of my normal distribution is my usual x theta, and my sigma is a function as well. My sigma is the logarithm of my measurements times some gamma, whatever. And then you estimate that directly. You don't need to do anything else. You can directly verify if this result is useful or if it isn't. You can use all the normal information criteria like ASC, BSC, whatever, and just compare this model to some way it didn't do that. You even can skip over the wall test and whatever. Yeah. This is actually Ruby's lava, although I hear there's quite some Python talks here, so why not in Ruby? The answer is quite simple. It misses a lot of the libraries around. The sad thing is, there is projects that actually started, like SciRuby and NMatrix, which is cool, and if you want to bring Ruby in the League of Numeric calculation, you can probably help those projects. And afterwards, one can decide to build the Markov chain on top of it. That's actually the smaller part. Implementing a good linear algebra and analysis library, that's the hard part. Yeah, that's actually it. I know I skipped over a lot of the details, but that's why I'm here and I'm answering questions. The question was how such a model can evolve when what happens in your data process changes over time. Okay, the answer to that is quite simple. You would actually set up this whole thing as what you would call a recursive Bayesian chain, and you can put in weights for aging data, so to speak. So you can build a model that uses what you learned before as prior for your current state, but is able to shift very old data out. So you will build a model that slowly adapts to changes. Because what you actually don't want to do is react very fast to changes, because a very fast change could mean that something is wrong. This is actually what you want to detect. But you do want to cut out data that is very old. So I hope that answers your question. Okay. The question was if the model can trend seasonality. Yes, you can. You can just write it directly in. For instance, a trend would mean that the data, for instance, rises over time. If you have a linear trend, it means that there is a component in the offset that gets bigger and bigger. What this usually means is that you're missing some information, because it doesn't happen normally, but you can just put it in. You can, if I find it, you can, at this point, what I use here is Theano. Theano is kind of a cool toy in Python. It is meant as functional language that provides something akin to lambda functions for mathematical expressions. So what I built here is, my view is t dot days times theta, and that is actually not evaluated, but it's built as a lambda function that can be minimized, optimized, whatever. And you could build horrendously complex things here. You can put a trend in, you can put, I don't know what it, moon phases, whatever you like. Okay?
What is the difference between your approach and, for example, using neural networks to train them on the set and use them to detect anomalies? Did you try that?
Okay. Question was, I don't remember, the question was why not use neural nets to detect anomalies. Personally, I don't use neural nets. I use support vector machines mostly, but that's my kind of approach. The thing is that it doesn't really tell you about. I mean, neural networks is a categorization approach. That means it could tell you about something being in a distinct state. It could tell you this connection code is high or it's low, it's medium or whatever. But it's not usually used for counts. What I have here is a count value where I don't know where it will be, so it doesn't have a categorical dimension. So what I'm using here is actually a regression problem that is more something that can handle loosely continuous data. I know it's discrete because it's count values, but I don't know what the high point will be. But in general, you can use this approach to optimize support vector machines as well. You can build here as a model the forward propagation equation of an RNA. Works just as well. Just takes a lot of time to compute, but it works perfectly. I did it actually.
Can you update the model with new data, or you have to rebuild it?
The question was if you can update this. In PyMC3, actually not, because MC3 is a Markov chain modeler, which means that it generates its sample data itself from a fixed set. So you would have to rebuild it, but you could use those models here. They are actually implementations of Poisson distribution that can be used in a Bayesian net and handles all the mathematical instability. So it handles very small values, very big values, and it handles the precision. And you could use those model classes to build a recursive Bayesian process that updates with each new sample. That is possible. At least I hear from guys doing it at Stanford with this tool that it is possible. I haven't tried it.
How do you decide on the threshold? How do you decide the threshold of something is anomalous?
Okay. The question was how to decide the threshold. That is basically arbitrary. You usually define a threshold as a probability limit that you would like to know. For instance, you decide that you want to know an event that is less likely than 1 in a million. So you set a probability limit that actually is this is a probability mass function, and you would use a point here where the mass of all points right of it is less than 1 in a million, and that is your limit. So there is no correct answer to this. It's basically weighting between high false positive rate and high false negative rate. So find your sweet spot, basically. And I know this is not a very satisfying answer, but yeah. Okay. Anything else?